Have you ever wondered whether the model you use is accurate enough? Or perhaps you're wasting your time using a model that is too sophisticated. In this video, we will present easy and complex models. There are two learning objectives. First of all, we explain why we need different model complexities, and second, we discuss how we can combine easy and complex models efficiently and robustly. Let us start with an example. Suppose that we have a generator. We can simulate it with a simple model as given here, but we can also zoom in on the different parts and see more details. For instance, we can look at the differential equations that represent the synchronous generator. Or, as you can see, even a simple block as the PSS can be complex. So, we can simulate a generator with a comprehensive model to describe its behavior accurately. But do we need this level of detail, or can we simplify this model? To determine this, we have to look at the application. In the first case, the model is used for grid expansion planning. Here, we want to find out which types of wind turbines or which types of pipelines we need in, say, 10 years. Usually, it's not needed to have a detailed description because we are only interested in the general trends. For instance, we want to know how the consumption is increasing, linearly or quadratically, so that we can invest appropriately in offshore wind farms. Then it is sufficient to have only a global overview and no detailed model is needed. In the second case, system operations, this is entirely different. Here, for example, we are interested in seeing the impact of an event on the grid dynamics. So we must know what happens exactly, not only now, but also in 5 or 10 minutes. Thus, the model should be more accurate. However, there's always the question, what is accurate and complex enough for the task at hand? The answer depends on the job, but grid planning generally requires simpler models, while grid operations demand more complex ones. Now let's take a look at two different models for computing the power flow in the electricity network. We have the alternating current model, or AC for short, and the direct current, or DC model. We start with the alternating current model. It leads to a non-linear system, which means that it's also more difficult to solve. On the left, we see the inputs, which are the topology, the generator power, and voltages and the demand. The output of this AC model is the current and power flow in the lines, the voltage at the nodes, the power losses in the system, the generator reactive power set points, and the power output at the slack bus. So, this model is complicated but comprehensive. Then we have the DC model. This model takes fewer inputs and has fewer outputs. As a result, we get a linear model that can be solved easily to give a rough estimate of the power flow, but sometimes this is not accurate enough. When comparing the two models, we can see the following 4 differences. In terms of complexity, the AC model is more complex, while the DC model is simpler. But the accuracy of the AC model is higher, thus this model accurately represents what has happened in reality. The AC model is nonlinear, which means that it's more challenging to solve. So solving this model will require more computational power and CPU time. On the other hand, the DC model is linear and relatively easy to solve. Finally, let us take a look at suitable solvers. Because the DC model is linear, we can use more straightforward mathematical solvers. The AC model requires complicated iterative solvers to solve this nonlinear model efficiently. As you can see, both the easy and complex models have their advantages and disadvantages. But is it possible to combine them? Is it possible to have the accuracy of the complex model and the speed of the simple model together? The answer is yes. We start with the inaccurate model. First of all, we solve that model. Then we use that solution as the starting solution of the accurate model. Afterwards, we check if that solution is accurate enough. If not, we can reiterate. We go back to the inaccurate model, solve it again, plug it into the accurate model, etc. If the solution is good enough, we can stop. We can not only use this combination of models in simulation, but also in optimization. In optimization, we try to find an optimal solution to a problem. It is not always needed to start the optimization with the accurate model. We can start with the inaccurate model, try to optimize that, plug that solution into the accurate model, and reiterate. This way, we can get a good enough solution in a fraction of the time. There are 3 challenges. First of all, the performance. Some models are easier to solve than others. We have to make sure that the models we are using are solvable within an acceptable time limit. Second, such problems or models are interdisciplinary. It is needed to have a clear view of the different components and closely cooperate between them. On the one hand, we need to consider the physics and electronic laws governing the physical behavior. On the other hand, computer science develops good solvers and efficient algorithms that can be implemented on modern hardware, and mathematics is at the core of all of this. The third challenge is inherent to the iterative way of solving models. How do we know when to stop? When do we consider the solution to be accurate enough? The answer is not straightforward and should be tuned to the problem. Let us recap. We have seen that different applications require different types of models, some more complex than others. Planning uses only general trends, while operations require an accurate system model. As an example, we have shown the differences between the AC and DC models, both with their advantages. The AC model is more complex but more accurate, while the DC model is easier to solve. We have presented a method that efficiently combines easy and complex models to get the best of both worlds. Finally, we have discussed 3 challenges: ensuring good performance, close cooperation between disciplines, and stopping the simulation. Thank you for joining today.